We want to use the limit definition of derivative to prove that the derivative of a constant function is always 0. So a constant function is in this form, f of x equals c, where c is some constant. So here's one solution that comes up a lot. And my question is, what's wrong with this answer? There's some things that aren't quite right. So pause the video and think about it. What do you think's wrong? Well, first thing that went wrong was when they substituted for f of x plus h. When they substitute x plus h into the x of this function, there is no x of this function. So no matter what you plug in, you're still going to get c. So there's the first error is that f of x plus h is not c plus h. It is just c. So that's the first error. And then they kept going. And let's say they kept going, and the next thing they did here was they got h over h, which is actually fine. That step's fine. And then they went over here and got 0 over 0. But does h over h equal 0 over 0? It doesn't. All right? If I got h over h, that would be 1, not 0. So the second step error is that h over h is not 0 over 0. This is actually 1. So if they had gotten 1 as a solution there, then they would then should have gotten limit of h goes to 0 of 1, which would be equal to 1, which of course is not 0. So still not correct. And then the third thing that I want to bring up, and this is the most important thing, I think, this right here, does that equal 0? The answer is no. If you get a limit, if you're trying to solve a limit and you substitute in the number, I'm going to actually keep this general. So let's say x goes to a, and you substitute in a, and you get 0 out of 0, 0 over 0, what that really means is that the same factor is in the numerator and the denominator. That means that there's an a minus x minus a in the numerator, then denominator, there's also one in the numerator. So they have some common factor at a that is cancelable. So that's really a whole. So when I get 0 over 0, when I try to plug in my limit value, that actually tells me that I have a whole. Or I probably have a whole, most likely. Maybe there's somewhere else in the function that causes a different result, but most likely I have a whole if that happens, and I definitely have something I can simplify. So if you have a 0, 0, this is what I want you to get from this problem. I'll write this in big bold letters. If you get the limit and you try to evaluate a limit of f of x and you get 0 over 0, that means there's a whole. And you should simplify. All right, so here's another solution that I received. And my question now is, what's wrong with this answer? Well, they did the first step right, where they plugged in f of x plus h is c, and f of x is c, and they left that over h, so that part looks good. But when they subtracted, that part right here, that part's not right. C minus c is not c. It's 0. But let's assume that they were right and they moved on. And then they got here. When I see c over 0 is that equal to 0. So this is the second mistake. The second mistake is the one I really want to point out. This is the one that if you get a number over a 0, that's not 0. A number, any number over a 0 or a constant over a 0 when you're trying to take a limit, that means you have an asymptote. That's not an E, that should be a C. This should tell you, hey, I have an asymptote. This is a discontinuity that I cannot remove. This means that my limit, if I have a limit of as x goes to a of some constant over 0, that should be equal to infinity or negative infinity. And we would just have to figure out which one. So if you see c over 0, that's what you need to think. So that's my other conclusion here. I'm going to put this one in bold too. So if you see a constant over a 0, we'll write it like we did the last one. So if I try to take the limit of a function and when I try to do it, I get c over 0, that should tell me I have an asymptote. That means I have a vertical asymptote at x equal a. That's where I get the equation. Alrighty. Now, what is the correct answer? So how do we do this? What we really do is, well, the last person was correct on that first step, so we'll copy that, c minus c over h. So f of x plus h, that is c. And f of x is also c, so that's over h. And then c minus c is 0 over h. And then I can simplify 0 over h to get 0. And then I take the limit and notice now there's no h left to plug in. So I don't have to plug in a 0 for my denominator like this person did here. That never happens. Also this one too, actually. Both of these people did plug in a 0 when they took the limit into a denominator, which you can't do. So the denominator is gone though. So before I even take the limit, I already simplified and I got 0, and that's how I get 0, because the limit of a constant is the constant. So note that we never take, we never substitute the 0 in the denominator because we simplified until there was no denominator. So what we actually got, and this is the conclusion on this one, we got the limit as, well, we got h equals 0, but I'm going to generalize it to make x approaches a. And if you get the limit of a 0 over a constant, any non-zero constant, then that tells me, well, that's equal to 0. So that's my third conclusion here. So there's three things I want you to take out of this. So let's make a little box of those three things. So if I get a 0 over a non-zero number, any non-zero number, then I get 0. If I try to take a limit and I get 0 out of 0, that tells me I have possible and most likely a whole. It definitely means I have two factors that can cancel and I can simplify. And if I have any non-zero number over a 0, that tells me I have an asymptote. I have a vertical asymptote at x equals a. So these are the three things that help us with these limits that are 0 or infinity. So possible whole, that means that there's some factor, x minus a, that's in both the numerator and the denominator. And if I simplify, I can find it and cancel it. And that usually means a whole. And the green, the last one, if I have 0 in the denominator, this is after I've simplified. If I have a 0 in the denominator and I have a not 0 in the numerator, that means I have a vertical asymptote. And it actually, in fact, I'm going to add to this. This means that the limit would be either infinity or negative infinity. Okay, so now that we know these three situations, let's look at this other commonly missed problem. I gave you a little hint here to find the left hand and the right hand limits. And why do you think I did that? Let's see. Well, let's look at this problem and see where it fits. Where does it fit? Let's just try to take the limit and see which it fits in. Is it 0 over a non-zero? Is it 0 over 0? Is it non-zero over 0? Or is it something else entirely? Let's just try, because if it fits in one of these boxes, we know what to do next. So try to substitute as it is. So we go 3 minus radical 3, we're plugging in the 0 because a is 0, minus 0 squared over 0. That's 3 minus radical 3 over 0. Okay, so the numerator is definitely not a 0. The denominator is a 0. So that means I fit into this category. So let's highlight it green. So this fits into a non-zero over 0. So I definitely have a vertical asymptote. That means my limit has to be either infinity or it's equal to negative infinity. But how do I tell which one? Well, one thing we can do is a sign analysis. So that's, whoops. Yes, we'll leave that there. So I know that I'm going to put my asymptote on a number line here. So I know I have an asymptote at x equals 0, or x equals a. So whatever x is going to when I get my limit of a non-zero over 0, that's my asymptote. So my asymptote is at x equals 0, because that's what my limit is being checked at. So if I plug in a number that's close to 0, but just to the left of it, let's say maybe I'll test -1. If it's positive, that must mean that if it's very close to 0, then surely it will be, if it's positive, that means it's approaching the positive infinity. The way to know if I'm close enough is to see what would make this numerator 0. 3 minus radical 3, what would make that 0? And we'll do 3 equals rad 3. We need not after this. Those are just numbers. I'm thinking of this piece right here. If whatever makes this 0 might be a place that the sign changes, but that's never 0. So that means I could really test anything to the left of 0 and to see the if it's all going to be the same sign. So if it's positive, I know it must be going up. And if it's negative, it must be going down. So I'm going to do a test point on both sides of my asymptote to find out. So on the left, I'll test a -1, and on the right, I'll test a +1. So when I put in a -1 into the original function, well, let's see. I know that this is always going to be, let's see, if I plug in a -1, then I would get a +1 here. So that'd be 3 minus 1, which is 2, square root of 2. So 3 minus square root of 2 gives me a positive. And I'm plugging in a -1, so I get a negative in the bottom. So I have a positive divided by a negative, which gives me a negative. And that tells me that this function, the asymptote behavior, must be going down. And that tells me that the limit from the left, as x approaches 0 from the left of this function, is -infinity. Now let's test the right. So let's test a +1. So I'm going to put in a +1 here. I still get a positive number for the same reason as I did before, but now I have a positive denominator, plugging in 1 for x. So if this is now positive, then this asymptote must be going to infinity, so it looks something like that. So that tells me that the limit of f of x as x approaches 0 from the right is positive infinity. These are not equal, which means there's nothing I can put on this limit that would be the same. That if they were both going up, then I would put infinity. If they were both going down, then I put -infinity. But since they're going different directions, I have to say does not exist. So there's that limit. So you can see why we had to check left hand and right hand, because that's how we find out if it's going to positive infinity or negative infinity. And we do these little test points of using a sign analysis on both sides of the asymptote.